This is my title. So today I'd like to, give some overview on the theory of quantum thermalization. And so at first I'd like to introduce the motivation, introduction to the general field of this quantum thermalization. And then I'll give a brief review on the theory for this quantum thermalization. So basically, such a theory is called theory of ergodicity, and I will briefly introduce the classical version and quantum version of ergodicity theory. And then I proceed to explain some modern development on this field in the context of so-called eigenstate thermalization hypothesis. And then at this level, I will introduce my own contribution to this field. And then I will just conclude my talk with some outlook. Okay. So as an introduction, okay, so actually the thermalization is a kind of everyday experience. Okay, so suppose we have a box and there are many particles inside the box, and the box is separated by the separating wall here into the dense region and dilute region. Okay, and if we remove this separating wall, then we know that this particle system relaxes very quickly and to this stationary state, which is characterized by the homogeneous particle distribution. Okay, so this is kind of a thermalization process. We observe this kind of thermalization everyday experience. And the statistical mechanics tells that what is the physical property of this thermal equilibrium state. Okay, so statistical mechanics tells us that if you measure something in this equilibrium state, and the measured quantity is given by the statistical ensemble average. Okay? Microcanonic ensemble or canonic ensemble or grand canonic ensemble, depending on your particular situation. And then this kind of success of statistical mechanics raise a very fundamental question. Where does this statistical ensemble come from? Okay? So in other words, how come this many-body system converges to the thermal equilibrium state seemingly irreversibly, while the underlying microscopic dynamics is irreversible? Okay, this is a kind of fundamental question since the birth of statistical mechanics. Okay. So this is a very important question and fundamental question, but usually when you have this kind of fundamental question, then usually the progress is very slow. Okay, so, but recently this fundamental question begins to attract growing interest, and that's mostly due to the fantastic advance in experimental side. Okay, so I will briefly introduce some representative experimental study along this line. So this is an experiment reported in 2006, okay? And they do some fantastic experiment with ultra cold rubidium atoms. Actually, they are trapped in this one-dimensional potential, almost harmonic potential. Okay, and then initially we have some, density packet here at the center of harmonic trap, and at time equals to 0, they give some impulse to these particle systems in such a way that half of the particle gains a momentum to the left, and half of the other particle momentum to the right. Okay, so at time equals to 0, this system is bring out of equilibrium or stationary state. Okay, and then they observe the time evolution of this density packet. Okay, so it looks very similar to the Newton's cradle. So actually, this system is called a quantum version of Newton's cradle. And then here they report this time evolution of this momentum distribution of this particle here. So this is the time zero, and time goes in this direction. Okay. So initially we have two set of particles, and then they approach to each other to the minimum of the potential well, and then they collide here. Okay, and then very surprisingly, even after this collision, we observe the reappearance of particle waves here. Okay, and then actually this density wave keep oscillating. They never approach to the thermal equilibrium state. Okay, so and actually this is the more quantitative analysis of this at the momentum distribution of this particle system, and they do not approach to the so-called Maxwell-Boltzmannian distribution of Gaussian. Okay, so this is kind of demonstration of non-thermal behavior of many-body system, even though they are strongly interacting. They are collide here. Okay. And of course, we have a very well understanding why this system do not thermalize, because the dynamics is too simple. Okay, so this is one of the example of integrable system, and we know that if there is even for the classical system, if the dynamics is integrable, then the system never thermalize. Okay, but this is so demonstration of this non-thermal behavior at the quantum regime. Okay? And later, these people, repeat a similar, experiment, the quantum Newton's cradle experiment, but they are using different atoms, dysprosium atoms. Okay, this atom has a very special property because their magnetic moment is 10 times larger than the rubidium atom. Okay, so that means they have a very strong interparticle interaction than the rubidium atoms. And moreover, if you apply some magnetic field, then this dysprosium atom aligns along this external magnetic field, and depending on this aligning angle, they can tune the interparticle interaction strength. Okay, so they show that if the interaction strength is very weak, then they also observe a non-thermal behavior. Okay? This is the distribution, time evolution of this momentum distribution. Okay, but if they tune the magnetic field and to increase the interparticle interaction strength, then they observe some very quick relaxation to the thermal behavior. Okay, so this is a demonstration that if even though you have a very clean quantum system, and if the interaction Hamiltonian is non-trivial enough, then you can observe the relaxation to the thermal equilibrium state. Okay. Then there is another experiment using the rubidium atom, and rubidium atom can be arranged in a one-dimensional array. So using some optical trap technique. Okay, so every site we have a single rubidium atom. Okay, and then if you apply some external laser, actually, I don't know the detail of this experimental technique, but somehow they can excite this rubidium atom to a highly excited Rydberg state. Okay, so basically this system becomes equivalent to the two-level system, ground state and excited state. And this Rydberg state, and it is known that this Rydberg state has a very strong repulsion with each other. So actually, in this setup, no two neighboring sites can be in the same Rydberg state simultaneously. Okay, so in the sense they are very strongly interacting with each other. Okay, and from experiment and some theoretical consideration shows that this system thermalizes at almost every energy eigenstate, but these people's experiment found that this system has a very special quantum mechanical state. For example, if you prepare this system in an antiferromagnetic initial state, antiferromagnetic means that ground state, excited state, ground state, and excited state. Okay, you can see the graphical representation of this initial preparation of your state. Okay? So this is the site index, and this is a time direction. Okay? So this is the initial preparation of your state, antiferromagnetic state, and then you do the time evolution starting at here. Okay. And then what they observe is that sooner or later, the system lose this antiferromagnetic order, but later on, this antiferromagnetic order resurrect, okay, and then disappear and reappearance, okay. So actually, there is some kind of coherent oscillation from this antiferromagnetic state. Actually, you can see that there is a phase shift here to there. Okay? We have two different antiferromagnetic state, and there is a coherent oscillation from one ordered state to the other ordered state. Okay? So this system is very special. Generally, this system is thermalizing, but it has a very special initial state that refuses thermalization. Okay, so this state is called many-body curve. Okay. So in quantum mechanical system, there are all kinds of different behavior in the context of thermalization. And actually, in the previous case, most studies remains at the level of some qualitative analysis. But this paper, I mean, performed a very nice analysis, even a quantitative analysis for the thermalization, okay? So they also use the ultra-cold atom system, and they prepare this rubidium atom in 2x6 optical lattice, okay? So here, this is a 2x6 optical lattice. And then they can tune the hopping probability of the, sorry. They can tune the, hopping probability of this rubidium atom by changing the laser intensity, okay? So initially they prepare this system in a kind of Fox state. Every site is loaded with just a single rubidium atom, okay? And then they reduce they increase the hopping probability, and then they do the time evolution, okay? So here, and then what they found is that, so initially the particle number distribution has a delta P gate here, okay? This is the initial preparation. Every site has a single particle. Okay? But in the steady state, what they found is that the number distribution has some broad distribution. And actually this is exactly matched with some theoretical prediction using this kind of a boson-Hubbard model, which is supposed to describe this rubidium atom, ultra-cold rubidium atom system, okay? So I guess this red bar is from the theory, from this boson-Hubbard model, and this dot coming from the experiment, okay? So even at the quantitative level, they report the thermalization of this quantum system. And furthermore, actually, one can ask, maybe this thermalization is coming from the decoherence from the environment, okay? So if you have a very big environment, which is in thermal equilibrium, then the thermalization is kind of trivial, okay? So they also report so-called purity. Purity means that they measure the trace of square density matrix, okay? So if the system remains in a pure state, then this purity remains, it must be identically equal to unity, okay? So this is their experimental report of the purity. So this is the initial purity, and even during the time evolution, the purity never decays. So okay, so this is an indication that this thermalization is only from the quantum mechanical nature of the system. not from the influence from the environment. Okay? So this kind of experimental study, I mean, triggers a lot of follow-up theoretical and experimental theories. I mean, and then in order to introduce the modern development in this direction, I first return to some historical development of the theory of ergodicity. Okay, so classically, the emergence of statistical ensemble is well understood from the ergodic theory. Actually, this hierarchy of classical dynamics was already explained yesterday. So actually, the ensemble average, the microcanonical ensemble, emergence of microcanonical ensemble can be understood from the ergodicity of the underlying microscopic dynamic rule. So ergodicity means that suppose I am interested in some physical quantity, which is a function of the phase space of the system. Okay, and then if you do some time average, okay, because of the dynamics, we have some the particle moves in the phase space. Okay, and then you can consider this kind of time average. Okay, and then you can, but the microcanonical ensemble is coming from this. This integration of all phase space. Okay, so in order to have the equivalence of this, actually this equivalence is called the ergodicity, and this happens when the particle fills the entire phase space uniformly. Okay, and this property is called ergodicity, and actually this ergodicity guarantee this microcanonical ensemble theory. Okay. And we know explicit example which satisfy this ergodicity. I mean, the most representative example is the simple harmonic oscillator. Single particle harmonic oscillator. And harmonic oscillator just circulate the phase space, and it fills the all accessible state. Okay. But actually, this is not enough because, as I told you, the simple harmonic oscillator, it fills all the entire phase space, but at any moment it is far from the thermal equilibrium. Okay, it at a single moment of the time, it just sit at a single phase space point, not the entire phase space. So actually, we need actually more strong condition. Which the condition is called mixing. Okay, mixing means suppose this is a phase space. And then we prepare a certain ensemble of our physical system, denoted by this black drop of ink here. And ergodicity means that this drop, fills the entire entire phase space. But mixing means that this, every single point of this the black ink just spread uniformly throughout the entire phase space. That's the idea of mixing. Okay, actually, this mixing guarantees the approach to the thermal equilibration. And this is a classical theory of equilibration. And then what about the quantum mechanical system? And actually, this problem was approached asked by von Neumann a very long time ago. 1929. Okay. Actually, it is from the very beginning of the birth of quantum mechanics. Actually, the von Neumann tries to reconcile the quantum mechanical time evolution with the statistical mechanics. So he tried to somehow prove the microcanonical ensemble theory starting from the unitary time evolution of the quantum mechanics. Okay. So actually, this original paper was written in German, and lately it was translated in English here by these gentlemen. And actually, this paper give a very nice, review of this original article. And what is the setting for this quantum ergodic theory? So we have some isolated quantum system described by the Hamiltonian H, and with some definite energy eigenstate. then what would be the quantum mechanical analog of classical ergodicity? Okay. Then one may think, consider this, density matrix. Okay, so this is the full Hilbert space, okay? Full Hilbert space. And then suppose some microcanonical energy shell here, and then you just pick a random state, psi 0, inside this energy shell, microcanonical energy shell, okay? Then you can consider this statistical, density matrix of this final state here, and you just do the time average, okay? And then you can also consider this microcanonical density matrix, which is common for the statistical mechanics. And actually, this microcanonical ensemble density matrix is just given by this form, okay? And just using the analogy to the classical mechanics, you can ask whether this time average of this state is equal to the microcanonical ensemble density matrix. But obviously, the answer is no, okay? Because actually, this quantity strongly depends on the initial preparation of your state, okay? But there is no any initial condition dependence here, so we cannot have equality of these two quantities. So we cannot use the classical analogy. So instead, von Neumann just introduced suggest to use so-called micro subspace, okay? So actually, we are interested in macro systems, so we cannot measure every microscopic physical quantity. So instead, we can only access some macroscopic quantity. Okay, so from this assumption, he suggests to separate the whole energy shell into different regions, which is called macro subspace. Okay, and each macro subspace corresponds to the sub-Hilbert space corresponding to some macro state, which is characterized by some macroscopic measurable quantity nu. Okay, and then in this setting, what he proved is that for most Hamiltonian system and for most partitioning of this microcanonical energy shell into this macro state, and then what he showed is that every initial state, from every initial state, you can prove that the overlap of your final state with this any macro state is equal to the volume fraction of this macro state. Okay, this is the quantum version of ergodic theory of von Neumann. Actually, this is not automatically satisfied. So actually, there are many conditions. For example, the system should not have any energy degeneracy. And actually, in addition to that, there is another condition for the size of this macro state. So the total Hilbert space dimensionality should be very large, and also each size of each macro space should be large enough. So in that limit, he showed proved this kind of quantum version of ergodic theory. And actually, so von Neumann's version of quantum ergodic theory is revived recently under the name of theory of typicality. So some people end up with so-called canonical typicality, and some people end up with some normal typicality. Actually, this is kind of some refined version of von Neumann's ergodic theory. Okay, so up to now, so somehow we are successful. But this success relies on our notion of macro state. So we should divide. So somehow we need some macroscopic quantity. So now from the understanding up to now, some experiment and theory suggests that this kind of a classification of some physical system into two categories. Some system is thermal and some system is non-thermal. And I already explained some example of non-thermal system. If the system is non-thermal, if the dynamics is too much simple, okay? So for example, integrable system, okay? And there are some special state, which is called many-body scarce, which refuse to thermalize. And although I do not cover this topic, but many-body localization system also refuse thermalization, okay? And maybe there are many more, but anyway, the other side, we have some set of thermalizing system, and we believe that most of the generic isolated quantum system should belong to this class. And then now we are at a position to define the quantum thermalization more explicitly, okay? So what do I mean by quantum thermalization? Suppose I have an arbitrary initial state, maybe belonging to some microcanonical energy shell, okay? So here, Cn is just arbitrary, okay? We should expect that statistical mechanics should apply to every site, okay? Every quantum state, okay? And then we can calculate this quantum mechanical expectation value of some physical quantity from the standard. I mean, this is just a standard, okay? As you can see, this quantity explicitly depends on time here, and explicitly depends on your choice of your initial condition, okay? Then what is the lesson from the statistical mechanics? Statistical mechanics tells us that the measurable quantity, the actual measurement value should given by the microcanonical ensemble average, okay? Which is written here. I mean, the uniform average of energy eigenstate expectation value of this operator O, okay? Then quantum thermalization requires that this quantity should be equal to this quantity if you wait long enough. For example, actually I should add t goes to infinite limit here. Actually, this is a requirement of quantum thermalization. Actually, this is very hard to satisfy because as you can see here, we have some explicit initial condition dependence, but there is no initial condition dependence at all here. And also there is a time dependence here, but there is no time dependence here. So actually, this is a very strong requirement, I mean, the quantum thermalization. And, but recently, this gentleman has some clue how to achieve this quantum thermalization, okay? So actually, they propose this kind of hypothesis. And actually, this hypothesis is called eigenstate thermalization hypothesis. So the contents of the hypothesis looks like this. Suppose, so I have some observable, and then if you calculate the matrix element in the energy eigenstate basis here, and if this matrix element has this kind of structure, okay, then we have a quantum thermalization. Okay, so what is special in this hypothesis? Here, this is a diagonal component, and this is the off-diagonal component. First of all, this off-diagonal component is exponentially small in system size because it includes thermodynamic entropy here. And thermodynamic entropy is an extensive quantity, so this is exponentially small. Okay? And additionally, you can see here that the diagonal element depends only on the energy. Okay, there is no quantum number dependency here. Okay? This is very crucial. This is very crucial. So it can depend on the energy of your energy eigenstate, but there is no quantum number dependence. And from this, assumption, they can show that actually this quantity really, becomes equivalent to the microcanonical ensemble average. Okay, so and also so actually, this is the hypothesis for the Hamiltonian, not the operator. Okay, so the thermal system should have an energy eigenstate in such a way that the matrix element should have this kind of structure. Okay, and so if you use this ansatz, you can actually this hypothesis guarantees the quantum thermalization from starting from any initial state, even if you start from the energy eigenstate. So the consequence of the energy ETH is that the energy eigenstate itself, basically this is equivalent to the equilibrium statistical ensemble. Okay, you don't need to consider kind of ensemble of the system. Even if you start from this energy eigenstate, single energy eigenstate, that is basically equivalent to the microcanonical ensemble. Okay? So you can associate all kinds of thermodynamic quantity even to this pure state energy eigenstate. For example, you can associate the temperature to this energy eigenstate using this kind of condition. Okay. So for example, you can associate, you can assign every energy eigenstate to the temperature using this rule, and even you can associate the thermodynamic entropy to a single energy eigenstate using this entanglement entropy. You do not need to consider the statistical ensemble of your state in order to define the entropy. And also, up to now, I focus on the equivalence of the expectation value and the ensemble averaged value, but this energy eigenstate hypothesis, thermal hypothesis, even successfully explain the fluctuation dissipation theorem. Okay, so actually this ETH was tested in 2008. So Rigol et al. Consider this kind of system. They consider some this kind some lattice system. Looks weird, but anyway. So initially, he introduced 5 hardcore boson in this area, and then turn on the link of this bond at time equals to 0. Okay, so initially this system is definitely far from the equilibrium of in this entire system. Okay, and then what they after turning on this bond, and then he measures some physical observable quantity, and this shows a time evolution of a certain observable. Okay, so initially it is far from some equilibrium value, and it shows some relaxation to some value. And he compared this the stationary value with some microcanonical ensemble prediction. Okay, so you can see that actually it has a very, there is a perfect match to the microcanonical ensemble theory. Okay? And also he did some numerical verification of the ETH, and then since this work, and there are actually very many numerical, evidence which support the validity of ETH. Okay? So I do not review all the numerical verification of ETH, but at this moment I'd like to introduce my own contribution in this field. So in the previous page, I said that the consequence of ETH means that we can do the statistical mechanics or thermodynamics even at the level of energy eigenstate. Okay, so here in this work, I consider so-called energy eigenstate Joule expansion. Okay, so I consider the one-dimensional XX chain. So initially, half of the chain is empty and half of the chain is fully occupied. Okay, and then at time equals to 0, I turn on the tunneling between these 2 compartments. Okay, this is just a free expansion type expansion, Joule expansion. And then this is a time evolution of a particle density. The blue curve for the right compartment and this red line from for this left compartment. Okay, so initially fully occupied and empty, and then they approach to the equilibrium state here. Okay, so also energy relaxed to the equilibrium state. And then what we found is that when we have this kind of Joule expansion in classical gas system, we have some Joule heating or Joule cooling depending on the nature of a particle interaction. And similarly, we observe this kind of Joule heating or Joule cooling depending on the interaction parameter of this XXG chain. So this shows a diagram. So this is an interaction parameter, and this line separate the cooling regime and heating regime. So for example, if I start from here at this interaction parameter and at this initial temperature, then the system cools down after this Joule heating, Joule expansion. But if you start from here, then the system heats up, okay? So probably this either can be used to control the temperature of ultra cold atom gas. And as I said before, we can also derive the fluctuation dissipation theorems only for using the ETH ansatz. So what is fluctuation dissipation theorem? So suppose you apply some perturbation to your system. So HT is the strength of the perturbation, and B is some operator leading to perturbation, coupling to this perturbation. And this perturbation lead to some response of some physical quantity. For example, A, the expectation value of A is influenced by the introduction of this perturbation through this kernel. And this kernel is called the response function. And actually, the fluctuation dissipation theorem relate the response function to the correlation function. Okay, so in classical system, the relation is very transparent, but in the quantum mechanical system, the quantum mechanical fluctuation dissipation theorem has some complicated form, but basically this reduces to the well-known classical version if we take h bar goes to 0 limit. Okay? And actually, this quantum mechanical fluctuation theorem can be expressed in terms of KMS condition. I mean, if the correlation function satisfies this kind of relation, then it guarantees the fluctuation dissipation theorem. Okay. So actually, this KMS condition was used to measure the temperature of the physical system. For example, if you take the ratio of these two quantity and take the logarithm and divide this quantity by h bar omega, and then this quantity should be independent of omega, and this value should be the temperature. So for example, so if you measure this quantity and draw the plot of this quantity, and if there is no omega dependence, that's the sign of thermalization. But if it has a omega dependence, this is a sign of indication of non-equilibrium condition situation of your system. So actually, we confirm this fluctuation dissipation theorem only using the ETH. So for example, if I start from a certain definite energy eigenstate whose temperature is given by here, and then we can formulate, we have formal expression for this correlation function using the ETH ansatz, okay? And then we can calculate this function. And what we found is that actually this ETH guarantees the fluctuation dissipation theorem here. Actually, this quantity is equal to beta. But unfortunately, there is some correction term, okay? But this correction term is, as you can see, so this is the order 1 quantity differentiated by this thermodynamic quantity. So basically, this correction to scale correction is just vanishes in the thermodynamic limit. Okay, so in that sense, we have this ETH, and this shows the numerical verification of this finite size effect. Okay, and recently we also studied the ETH study for the two-dimensional system. For example, we studied the two-dimensional XXG model. Actually, ETH has been tested for so many times, but mostly on the one-dimensional system. But there are only a few tried for in the two-dimensional system. Actually, I chose this particular system because it has a very this system has a very special property. For example, this XXG chain has a special non-abelian symmetry, so-called SU2 symmetry, when the spin-spin interaction is isotropic. So non-abelian means that it has a conserved quantity, the total magnetization in the x direction and y direction and z direction. But this different the magnetism in the different directions do not commute with each other. So it has a very special property, and we successfully show that this system also satisfies the ETH ansatz. But actually, there are some. We need to be very cautious because of this SU2 symmetry. So what we show that inside each SU2 sector, we have this ETH. That's the conclusion of my recent paper. Okay, this is it, and maybe I have my own list of future work. For example, as I said that we can do all kinds of statistical mechanical study or thermodynamics starting from at the level of energy eigenstates. So then, the natural question we can ask is, so what about the phase transition? Okay, so phase transition, we know that there are some critical scaling and critical exponent and something like that. Then I think that all the information should be included in the energy eigenstate. So probably this could be a very interesting topic, and also some other topics as well. Okay, thank you for your attention.
Thank you, Jae-dong, for this very nice lecture and review also of the history of ETH and thermalization. Questions, please. There's a question, Alexei.
Yeah, thanks for a nice presentation. I have a bit of a naive question. So how much of it carries over?
Mask off, please.
Yeah. How much of it carries over to the single particle systems?
Single particle thermalization of single particle system.
Yeah.
Well. So actually, the ETH means that isolated system become thermalized, because every local system, is thermalized under the action of the rest of the system. Okay, so but if you have only a single particle system, then there is no your partner which is thermalizing you. So I think single particle system just remains at the level of non-thermal, pure state behavior, which is very far from thermalization.
Okay, thanks.
More questions? Maybe I have one about the last 2D results you mentioned. What's the size of the system? Yes.
For two-dimensional system, the largest one is a 4x7. 4x7.
Thank you. And another question, you at the beginning in your review, you mentioned that there's also mixing, but essentially then you, as many others also, are focusing on the ergodicity aspect.
Yeah, right.
What about mixing?
Yeah, actually, I didn't explain enough. Actually, so if the title is the ergodic theory, but here already this mixing property was hidden. So actually, I said that there are some hidden conditions here. So if you assume there is no degeneracy in the energy eigenstate, and also so-called no resonance condition, because that means for any two pairs, the energy gap should not be equal to each other. This is called no resonance condition. Under this condition, then one can prove there is some rigorous proof for this the relaxation property. The time dependence vanishes.
Is that a way to, I mean, in classical systems, mixing, I thought, is essentially related to Lyapunov exponents. So is that a way you indicate how one can compute Lyapunov exponents in quantum systems, which is different from OTOG, for instance, or other similar approaches?
Yeah, as you mentioned, the OTOG is one candidate, and there is another candidate which is also called operator growth, which is partly mentioned by Dario. So actually, Schrödinger equation is just a linear theory, so we do not have this exponential type of divergence of your state. Okay, but if you focus on the operator itself, then operator can actually grow exponentially in some extended Hilbert space for operator. Okay, so actually there are some research in that direction.
Okay, thank you. More questions? Oh, Alexei, last question, please.
Yeah, what happens if you go to long range systems with long range interaction?
There are some works which deals with long range interaction. For example, I mentioned this dipolar interacting system. So they model this system using this Bosoni-Hubbard model, but with long range interaction, 1 over R to the some power. Okay, so even with this long range interaction, they show some ETH consistence with the ETH, but I'm not sure whether they have some systematic study depending on by changing the exponent of describing this power law. But at least there is some study on that on a particular system.
Okay, I think we have to stop here and move into the break. So let's thank Jae-Dong again. Thank you very much.
Thank you.